So here's the final week of the semester, and the subject is special relativity. So the video here will have two parts. Part one is on coordinate transformations, and that's this video. And part two is on energy and momentum, and that's the other video. So let's start with a little bit of history on Albert Einstein and the theory of special relativity. So here's sort of an introduction. Ever since the time of Galileo Galilei, that was back in the 16th century, 500 years ago, physics has had what's called the Principle of Relativity, which states that the laws of physics are the same in all inertial frames of reference. And Einstein started with that idea and combined it with the hypothesis that Maxwell's theory of electricity and magnetism is the correct theory and therefore must be the same in all inertial frames. And since Maxwell's theory predicts the speed of light, that would imply that the speed of light has to be the same in all inertial reference frames. So we'll see what consequences that has. Now we have to understand this concept of frames of reference. And the best way to approach this is to consider an example. Consider two observers in relative motion. For example, observer A is at rest on the surface of the Earth. So let's suppose this gray plane here is a region of the Earth's surface, and Mr. A is at rest at some point where he has his measuring devices. And then there's another observer. But observer B is in a railroad train that moves with velocity over the surface of the Earth. So here in the train is observer B, who has a set of apparatus for making measurements. But B is moving relative to A with some velocity v. We'll take it to be in the x direction. Of course, A is moving relative to B. Relative to B, A is moving in the opposite direction with the same speed. So velocities are always relative. When you say there's a velocity, you have to say, with respect to what? Now, the principle of relativity says the equations of physics should be the same for both observers. And we'll pursue this by assuming there's an oscillator present, a harmonic oscillator. You remember the equation for an oscillator. The mass times the acceleration is minus kx from mechanics. So, and the acceleration is the second derivative of the position with respect to time. So, this equation would be true. M d squared x prime dt prime squared is minus k x prime minus x0 prime at time t prime, where x prime is the coordinate of the oscillating mass as measured by Mr. B. This mass is oscillating. It's oscillating back and forth. And in his frame of reference, the mass has a position x prime. And he's observing the motion with a clock, with a watch, which corresponds to a time t prime. So x prime and t prime are position and time coordinates, as measured by the equipment in the lab of Mr. B. X0 prime is the equilibrium position of the oscillating mass, as measured by B. So x prime minus x0 prime is the displacement from equilibrium, as measured by B. And we have here mass times acceleration is minus k times the displacement. Well, that's how B would observe the oscillator. But now let's suppose A observes the oscillator. Maybe have one observer, A, and he has a telescope or something where he can look inside the train and watch the oscillator as it oscillates inside the train. Or maybe I have a set of observers who are all at different points on the system, on the surface of the Earth, and they're all watching the accelerator, they're all watching the oscillator and taking data, and then at some later time they get together and compare their data. According to the principle of relativity, m d squared x dt squared must be minus k x minus x0, where x and t are the position and time coordinates measured by the equipment at rest on the surface of the Earth. Both of these equations must be true by the principle of relativity. Now here's a little theorem about that problem of the mass m oscillating because it's attached to a spring. So here's the spring K. And this is maybe the equilibrium position. And the mass is oscillating around the equilibrium position. So it's displaced from the equilibrium. And we want the equation, mass times acceleration is minus k times the displacement. We want that to be true in both frames of reference. And the theorem is, it is true if the coordinates are related by what's called the Galilean Transformation. The Galilean Transformation says t prime is equal to t. The time coordinate is the same in both, for both observers. And x prime is x minus vt. Of course, the space coordinate is not the same for both observers because this whole system is moving relative to the Earth. So the coordinate of the position coordinate would be different. It would depend on time for the two observers in different ways. And the relation for the Galilean transformation is x prime is x minus vt. So for example, if we take the equilibrium position of the oscillator, x0 prime is x0 minus vt. Everything here is moving relative to the Earth with a velocity v in the x direction. In particular, the equilibrium position is moving. So x0 prime is x0 minus vt, or maybe a better way to look at it, x0 is x0 prime plus vt prime. So for example, if the equilibrium position were at the origin of the coordinates used by Mr. B, well, that whole coordinate system is moving with a velocity v, so the position in the coordinates of Mr. A would be Vt prime. Well, T prime is the same as T. So you can just say, as well say Vt. Not at the origin, it's moving relative to the origin with a velocity v. And we can prove this theorem. We want to consider m d squared x dt squared, mass times acceleration, as measured by observer A. Well, the second derivative, well, first of all, t prime and t are equal. So d squared x dt squared is the same as d squared x dt prime squared. Because t and t prime are the same. And x prime is a linear function of t, or the difference between x prime and x is a linear function of t. So the second derivative is 0. So the second derivative of this term, well, the first derivative of this term would be minus v, or minus v. But v is a constant. So in these inertial frames, the relative velocity is a constant. These are not accelerating with respect to each other. These are only moving with constant velocity. Therefore, they're both inertial frames. So inertial frames have a constant relative velocity. What's meant by an inertial frame? It's a frame of reference in which Newton's first law, the law of inertia, is true in both frames. Well, that will be true if they're moving with constant relative velocity. An object at rest remains at rest. Or an object in motion remains in motion with a constant velocity. That's Newton's first law of motion, the law of inertia. So the second derivative of x prime is 0, because v is constant. Now m d squared x prime dt prime squared is minus k x prime minus x prime 0. That's the equation of motion as observed by observer B. But now let's put in x prime as x minus vt, and x prime 0 is x0 minus vt. And, I can use x0 prime is x0 minus vt. x0 prime is x0 minus vt. I could say minus vt or vt prime. It doesn't really matter because t and t prime are equal in the Galilean transformation. So we have minus kx plus kx0, and the t and t prime cancel. Here's minus vt plus vt prime, but t and t prime are equal. So I just get minus k x minus x0. That proves the theorem. The equation of motion observed by observer A is the same as the equation of motion observed by observer B. The coordinates aren't the same. There's a set of moving coordinates. But they're related by this Galilean transformation. Now that seems pretty basic and pretty simple. So why has Einstein come into the act? Maxwell's field theory is not the same for both observers if you relate their coordinates by the Galilean transformation. So if the two coordinates systems were related by the Galilean transformation, this transformation, then Maxwell's field theory would not be the same for both observers. And the easiest way to think of that is Maxwell's field theory implies a speed of light. And the speed of light is just a constant. It's 3 times 10 to the 8 meters per second. So if Maxwell's field theory is true for both observers, the speed of light would have to be true for both observers. And Einstein asked this question. Suppose the speed of the train is equal to the speed of light. So this isn't some ordinary earthbound train. This is some kind of science fiction train that travels at the speed of light. Then observer A would measure the speed of light to be c, our usual 3 times 10 to the 8 meters per second. And what would observer B measure? Well, according to the Galilean transformation, which for the moment we're assuming is correct, the phase velocity of the light waves would be delta x prime over delta t prime, using the coordinates of the measurements made by observer B. X prime is x minus vt, so you have delta x minus vt. T prime is the same as t, so we'd have divided by delta t. Well, delta x divided by delta t is c. That's this equation. And delta vt divided by delta t would be minus v. So you see the velocity of light in the train would not be the same as our usual 3 times 10 to the 8 meters per second. In fact, if the train were moving at the speed of light, then the phase velocity of the light would be 0. Relative to observer B, light would not move. But according to Maxwell's theory, dx prime dt prime is 1 over the square root of mu 0 epsilon 0, where these are the usual force and constants for magnetism and electricity. And that's just c. And there's no way that this can be anything other than c if Maxwell's theory is correct in any frame of reference. So something's got to be wrong, because according to the Galilean transformation, the phase velocity would be 0. But according to Maxwell's theory, the phase velocity would be c. And at the time of Einstein, most people believed that Maxwell's theory is not complete. Maxwell's theory must be valid only in a certain frame of reference with an ether, a material or something, not exactly material, not material made of atoms, but some kind of material thing, some kind of stuff called ether. And Maxwell's equations would be true if the laboratory is not moving through the ether. But if the laboratory is moving through the ether, then Maxwell's theory would not be, Maxwell's speed of light would not be the same. It would transform according to the Galilean transformation. The reason Einstein is thought of as a great genius is Einstein said, everybody else is wrong. There is no ether. There is no ether, and Maxwell's theory is true in all frames of reference. Those equations, those 4 equations, which give us electromagnetic waves, and the Galilean transformation is what's false. Now, the Galilean transformation had been around since the time of Galileo, and we just saw in the previous example, it's correct for Newtonian mechanics. So what Einstein was really saying was, Newtonian mechanics is not the full exact theory of motion. So, which prediction is correct? Is the speed of light the same in all frames of reference, or does it depend on the motion through the ether? The fact is, B would measure delta x prime over delta t prime equal to c, same as A, because the laws of physics are the same in all inertial frame, including Maxwell's theory of electric and magnetic fields. At the time that Einstein published this, 1905, what's that, 115 years ago, he was the only person in the world who understood this. And everyone else believed there was some kind of ether. But Einstein made certain predictions based on his ideas. And before long, Einstein's theory of relativity was a part of physics. All right. So according to Einstein, the problem is this. The Galilean transformation, the transformation of position coordinate x to x prime and time coordinate t to t prime, where x prime is x minus vt and t prime is t, that transformation, which goes back to the time of Galileo, that's not the correct transformation between space and time coordinates in our universe. And the way he concluded that is that he said Maxwell's theory must hold in all frames of reference, and therefore the speed of light must be the same in all frames of reference. Now, okay, if this transformation is not correct, what transformation is correct? And the correct transformation had actually been written down before Einstein by the famous German physicist Lorentz, Hendrik Lorentz. And Lorentz didn't quite understand what he had. It took the genius of Einstein to understand the consequence of the Lorentz transformation. All right, so we're going to look at the Lorentz transformation. The correct transformation between space and time coordinates of inertial frames in relative motion is given by these equations. Making a transformation x to x prime from the coordinates in the Earth's frame of reference, A, to the coordinates in the train's frame of reference, B. X prime is not x minus vt. It's a certain constant times x minus vt. And the constant is 1 over the square root of 1 minus v squared over c squared, where v is the velocity of the train and c is the velocity of light. Now you can see why that's very close to the Galilean transformation, because any train travels much slower than the speed of light, except some science fiction train. But in any real train, gamma is going to be essentially 1. Or to a very high approximation, gamma will be 1. And so then we'd be back to the Galilean transformation. X prime is x minus vt. But then there's more. The times measured by the two observers are not the same. The time coordinate of A transforms into t prime, which is gamma t minus vx over c squared. Or this is the same gamma, and this is the velocity times the coordinate divided by the speed of light squared. Now again, if everything moves slow compared to the speed of light, gamma would be approximately 1, vx over c squared would be approximately 0, and we'd have t equal t prime. But not everything moves slow compared to the speed of light. There are particle accelerators which accelerate particles to almost the speed of light, almost as high as the speed of light. And so this is the correct transformation. Now I'm writing this equation for relative velocity in the x direction. So v vector is v scalar times I hat, or not v scalar, but v, the component in the x direction, is a constant c. And v, the vector direction, is along the x-axis. That tells me how the x-coordinate transforms. How do the y and z coordinates transform? Well, y prime is equal to y and z prime is equal to z, the coordinates don't transform. The coordinates perpendicular to the velocity don't change. It's the coordinate parallel to the velocity, in this case in the x direction, which undergoes this change. But for coordinates in the perpendicular directions, y and z, they would be the same for Mr. A or Mr. B. Now, when I say this is the correct transformation, what do I mean by correct? What I mean is that's the transformation such that the laws of physics are the same in both frames of reference. Now let's consider an example. Let's consider as an example the origin for observer B. In other words, x prime, y prime, and z prime are 0, 0, 0. These are the coordinates of B. These are the coordinates of the origin in the frame of reference of the train. So you might take this to be, the center point on the train. Then what are the coordinates in the Earth frame of reference of that point? Well, what are the space coordinates? Well, x prime is 0, and x prime is gamma x minus vt. So x is vt. Y prime is 0, because y prime is 0 at the origin. And y prime is equal to y. So y is also 0. And z prime is 0, z prime is equal to z, so z is 0. So the answer to the question is x, y, and z are vt 0, 0. That is to say, the origin of the coordinate system on the train is moving with a velocity v I hat relative to the Earth, or relative to the inertial frame of observer A. So this transformation has the correct relationship of relative motion. Namely, both frames of reference. No, the relative motion of the two frames of reference is v I hat. So that was one condition on the transformation, and that works for this transformation. This transformation is rather simple because it's linear. X prime only depends on the first power of x and the first power of t. Similarly, t prime only depends on the first power of t and the first power of x. So it's a linear transformation, and it has this form that any point, or in particular the origin of the frame on the train, is moving with a velocity v I hat. Now let's do another example. Let's show that for this transformation, the speed of light is universal. So that's really the statement of the theory of special relativity. The speed of light is universal. It's the same for all observers. It doesn't depend on the relative motion of the observer relative to other inertial frames. Well, let's prove that this is true for this transformation, meaning that this is the linear transformation that I'm looking for. Well, I can calculate the speed of light in the coordinates of the Earth. V would be dx dt, where dx is the distance traveled by some phase point on the wave, maybe a crest on the wave during a time dt, and that would be c. By definition, that's the speed of light on the surface of the Earth, c. Now, what's the speed of light as measured in the train? Well, it would be dx prime over dt prime. It would be the distance divided by the time. The distance traveled by, let's say, a crest on the wave, here we have this wave. It has crests and troughs. And this is the crest moving with the velocity v. Or as measured by observer B, v prime. dx prime, it's the distance that the crest moves in a time dt prime, where the distance and time are measured by observer B. Now dx prime, well, dx prime will be gamma. Gamma doesn't depend on time. Gamma is a constant, because I said the velocity is constant. So dx prime will be gamma dx minus v dt. So here's dx prime, gamma dx minus v dt. And dt prime, gamma is a constant, v is a constant, so these Lorentz transformations are only for constant relative velocity. dt prime will be gamma dt minus v over c squared dx. So dt prime is gamma dt minus v dx over c squared. Divide the numerator and denominator by dt, or no, factor out dt from the numerator and denominator. Dx is c dt minus v dt. So I have gamma c minus v dt in the numerator. And in the denominator, dx is c dt. So I'll have dt minus v c dt over c squared. That's dt minus v over c dt. So I can factor out the dt. It's gamma 1 minus v over c dt. And now gammas cancel. The dt cancels. C minus v is c times 1 minus v over c. Then the 1 minus v over c in the denominator cancels that, and all I'm left with is c. So indeed, this transformation has the property that the speed of light is the same as measured by observers A and B. And since A and B are kind of arbitrary, the speed of light would be the same in any inertial frame, any frame moving with a constant velocity relative to, let's say, the Earth. In fact, we could go through more mathematics. I won't do it, but this is the unique transformation, the only transformation which is linear, satisfies this relative velocity condition, and satisfies this universal speed of light condition. So if you demand a transformation which is linear, has relative velocity v I hat, and a universal speed of light, this is the only transformation it can be. Now we'll look at some consequences of the Lorentz transformation. And the first consequence is called time dilation. So consider again two observers, A and B, in relative motion. A, well, we'll say A is at rest on the surface of the Earth. B is in a train that moves with velocity v I hat on the surface. Why do we use a train? Why don't we use a car? Well, in the time of Einstein, there were a lot of trains. Einstein lived in Switzerland at the time, and Switzerland is famous for its trains. So Einstein, wanting a relative motion, he naturally thought of a train. When Galileo wanted to describe relative motion in terms of an example, he tended to use a sailing ship, because at the time of Galileo, there weren't any trains. But I guess in the year 2021, if we want relative motion, we could talk about an observer at rest on the Earth and an observer moving in a spaceship. But that's not very realistic. I mean, there aren't very many laboratories in spaceships, just maybe the space shuttle or something, the International Space Station. So we'll stick with Einstein's language and say the relative motion comes because the laboratory of observer B is on a train. moving along the x-axis, let's say. Now let's suppose that observer B has a watch that ticks every second. In his frame of reference. So the first tick occurs when the coordinate t prime is equal to, let's say, some number tau. So that's, at a time tau, B observes his clock tick. And let's suppose that at that time, his position is the origin in his coordinate system, in the train's coordinate system. So let's say the first tick occurs at time tau and x prime, y prime, z prime equals 0, 0, 0. Now the second term occurs at the same position because the watch is not moving relative to the train. The watch, Mr. B is holding the watch in his hand and he's at rest on the train. So the watch will still be at the origin in the coordinate system of the train. It'll have x prime, y prime, z prime as 0, 0, 0. And what will be the time? Well, it'll be tau plus 1 second. 1 second later, 1 second as observed on the train, the clock ticks again. So that's the second tick. Now let's ask, where and when does Mr. A observe the two ticks? Now, of course, the watch is moving relative to Mr. A, so you have to sort of think of having multiple observers on the surface of the Earth who are all observing the clock and getting together later on and comparing their times. Or maybe you could say, well, Mr. A has a special observing device which observes the ticks of the clock. Well, the first tick, okay, so we had a relationship between x prime, t prime, and xt. For example, we had x prime was gamma x minus vt. And similarly, t prime was, again, this constant gamma, and then t minus Vx over c squared. Vx over c squared. Well, that's a transformation from xt to v to x prime t prime. If I know x and t, I calculate x prime and t prime. Here I want the opposite. I want the transformation, since I know x prime and t prime, I want to go from x prime and t prime to x and t. So I want the inverse transformation. Well, it's just a linear set of equations, so it's just a matter of algebra to write equations for x in terms of x prime and t prime, and t in terms of x prime and t prime. It's really the same transformation, but with the velocity in the opposite direction. This is for relative velocity v. I want the transformation with relative velocity minus v. Frame x moves with a velocity minus v relative to the train. The Earth's frame is moving relative to the train in the opposite direction from the direction in which the train is moving relative to the Earth. So it's the same transformation, it's the Lorentz transformation, but change the sign of the velocity. So x would be gamma x prime plus vt prime, and t would be gamma t prime plus vx prime over c squared. Now, the first tick occurs at x1 is gamma x prime is 0, v t prime is tau. So x1 is gamma v tau. And t1, the time when Mr. A observes the first tick, is gamma t prime plus vx prime over c squared. X prime is 0, t prime is tau. So t1 is gamma tau. Those are the coordinates, position and time coordinates, of the first tick of the clock. Now let's look at the coordinates for the second tick of the clock. Well, again, x is gamma x prime plus vt prime, but now x prime is still 0, but t prime is tau plus 1. One second later, in the frame of reference of Mr. B. And t2 will be gamma t prime plus vx prime over c squared. Again, x prime is 0, t prime is tau plus 1. So it's gamma tau plus 1. Now here's the time dilation. T2 minus T1, take this minus this, is gamma t plus 1 minus gamma t. It's gamma times 1 second. Remember what gamma is? It's 1 over the square root of 1 minus v squared over c squared. So T2 minus T1 is 1 second divided by the square root of 1 minus v squared over c squared. Now, the denominator is less than 1. So this is greater than 1 second. So the time interval is longer for Mr. A by the factor gamma, 1 over the square root of 1 minus v squared over c squared. So let's suppose Mr. A has an identical watch. When he observes the 2 ticks made by the watch of observer B, he will say, Mr. B's watch is running slow. But there's nothing wrong with Mr. B's watch. Mr. B's watch is running normally. But there's a coordinate transformation between the times. So a time interval of 1 second to Mr. B is longer than 1 second as observed by Mr. A. Let's look at some numerical examples of time dilation. So here's the time between the 2 clicks in the frame of the train. 1 second. And here's the speed of the train compared to the speed of light. So this is the speed of the train measured relative to c. Well, let's say 1/10 of the speed of light, or half the speed of light, or 90% of the speed of light, or 99% of the speed of light. Of course, terrestrial trains don't move that fast, but we're taking this to be some sort of idealized thought experiment where these are science fiction trains. Now, gamma is 1 over the square root of 1 minus v squared over c squared. That will always be a number greater than 1. Gamma is 1 over the square root of 1 minus v squared over c squared. The denominator is less than 1, so 1 over the denominator is greater than 1. Well, for a speed of 1/10 of the speed of light, gamma is 1.005. At a half the speed of light, gamma is increased to 1.155. At 9/10 of the speed of light, gamma has increased to 2.294. And at 99% of the speed of light, gamma is 7.089. So as the speed of the train increases, and especially as it gets close to the speed of light, the time dilation factor, gamma, increases more and more. In fact, as v approaches c, gamma approaches infinity. So if V over C were infinite, which is of course not possible, but if if V over C were 1, which is in fact not possible, but you can approach 1, but if you really made it 1 in the formula, you'd find the time dilation would be infinite. Now, of course, the time measured by the observer at rest on the Earth would just be gamma seconds. 1.05 seconds, 1.15, 2.29, 7.09 seconds. So measured by observer A, those are these measurements, he would say the 2 ticks of the clock are greater than a second. The clock must be running slow. Okay, so time dilation. The time coordinates of different observers are different. The other immediate consequence of the Lorentz transformation is called Lorentz contraction. That has to do with lengths. Let's suppose that Mr. B has a meter stick. And the meter stick, he's holding it in his hand, it's moving along at a velocity v relative to the Earth. The coordinates of the ends of the meter stick at some time t prime are x prime, y prime, z prime is 0, 0, 0. So the left end of the meter stick, let's say, is at the origin. And the right end of the meter stick would then be at x prime, y prime, z prime equals 1, 0, 0, 1 meter, 0, 0. These are the measurements according to Mr. B, who's riding along in the train. And now let's ask, what are the coordinates of the ends at time t in the Earth's frame of reference? Of course, the observer in the train would look at the position of the left endpoint and the right endpoint at the same time. So this would be the same time for both observations. Now let's say that the observer on the Earth looks at the coordinates of the ends at the same time, t. In other words, the left-hand side, he'll measure it at time t. The right-hand side, he'll also measure it at time t. What are the coordinates that he measures with in his frame of reference, the Earth frame of reference? Well, the left end will be at x, which is gamma x prime plus vt prime. Now x prime is 0. And t prime is gamma t minus vx over c squared. So here's the transformation from t and x to t prime. Here's the transformation from x prime and t prime to x. I have to use both of those transformations. They are the same except for the sign of the relative velocity. So the left hand will be at gamma v gamma t minus vx over c squared. Now that occurs at some time t. I haven't really specified the time t. So let's solve for x. Let's solve this equation for x. So you have x on this side of the equation. On this side of the equation, I have minus gamma v squared over c squared x. So let's move this to the other side of the equation. On the left side of the equation, I'll have x, 1 plus gamma squared v squared over c squared. And on the right-hand side of this equation, I'll have gamma v gamma t, gamma squared vt. Or I want to solve for x, so let's multiply both sides of the equation by gamma to the minus 2. On the right-hand side, I'll have vt. On the left-hand side, I'll have x, gamma to the minus 2 plus v squared over c squared. Now, gamma to the minus 2 is 1 minus v squared over c squared. Remember gamma? Gamma is 1 over the square root 1 minus v squared over c squared. T squared. So 1 over gamma is the square root of 1 minus v squared over c squared. Oh, sorry, no t squared. C squared. So 1 over gamma is the square root of v squared, 1 minus v squared over c squared. So 1 over gamma squared, that's gamma to the minus 2, is 1 minus v squared over c squared. So I have here 1 minus v squared over c squared plus v squared over c squared. Sorry, I'm working on this equation. No, this equation. Gamma to the minus 2 times v squared over c squared is 1. So I have here x is vt. Well, I already knew that because the meter stick is moving with velocity v relative to the Earth. So I already knew the position of the origin would be vt, and the left side is at the origin. But now let's look at the right end. The right end is x is gamma x prime plus vt prime. Same t prime, because the coordinates for the coordinates measured in the train frame of reference are at the same time, the same train time. And now x prime is 0. And t prime is one meter. Oh, sorry, x prime is not 0. X prime is 1 meter, because I'm looking at the right end. So I'm looking at the right end, x prime is 1 meter. And t prime is, again, v gamma t minus vx over c squared, where this is the same t as for the observation of the left end, but this is now the position of the left end, of the right end. So this x is the position of the right end. This x is the position of the right end. In the other calculation, x was the position of the left end. But in this position, x is the position of the right end. So now again, let's solve for x. I can move this term to the other side of the equation. I have gamma v minus gamma over c squared, move that to the plus other side of the equation. I'll have plus gamma squared v squared over c squared x. And then on the right-hand side, I have gamma times 1 meter plus gamma times v gamma t. So I have gamma squared vt. And now multiply both sides of the equation by gamma inverse. No, gamma to the minus 2. So on the right-hand side of the equation, I'll have vt here, gamma squared divided by gamma squared is vt, plus gamma over gamma squared times 1 meter. That's 1 over gamma times 1 meter. So this term, which I didn't have in the other case, because in the other case, the position x prime was 0, but in this case, When I divide by gamma squared, I'll have 1 meter divided by gamma. Gamma to the minus 1 times 1 meter. And on the right-hand side of the equation, I'll have gamma to the minus 2 plus v squared over c squared. And again, gamma to the minus 2 plus v squared over c squared is 1. So you see I have 1 is Vt plus 1 over gamma, that's the square root of 1 minus v squared over c squared, times 1 meter. So in meters, the coordinate is Vt plus the square root of 1 minus v squared over c squared meters. All right, so what's the length of the meter stick as observed by Mr. A? Well, I would take the distance from the right end minus the distance from the left end. So the distance from the right end minus the distance from the left end is this minus Vt. The Vt cancels. It's the square root of 1 minus v squared over c squared meters. So this is the length of the meter stick as observed by the observer on the Earth. This is a number less than 1. So it's less than 1 meter. Now, of course, Mr. A has an identical meter stick, and he will think that B's meter stick is shorter. So that's called Lorentz contraction. It's been contracted by the factor 1 over gamma, square root of 1 minus v squared over c squared. So again, let's work out some numerical examples of Lorentz contraction. What's delta x prime? Well, it's 1. It's 1 meter. So that's the coordinate difference between the left end and the right end as observed by Mr. B. So that's the prime. And let's compare that to delta x, the distance between the right end and the left end, as observed by Mr. A. And let's do it for different values of velocity. Let's say 1/10 of the speed of light, half the speed of light, 9/10, 0.99, 99% of the speed of light. We have these values of gamma, or now I need the value of 1 over gamma, will be 0.995, 0.866, 0.436, 0.1411. So you see, just as in time dilation, the time dilation factor increases with the speed. In the case of Lorentz contraction, the Lorentz contraction factor, which is 1 over gamma, decreases with relative speed. And so the length of the meter stick as observed by Mr. A would be 0.995, 0.866, 0.439, 0.1411. And in fact, as the velocity, relative velocity goes to the speed of light, the length of the meter stick appears to be 0. Or let's better say, approaches 0. So as V over C approaches 1, the contraction factor approaches 0. So time dilation and Lorentz contraction. In a frame of reference in which a watch is moving with velocity v, the time dilation factor is gamma. And so the time between successive ticks is larger than 1 second. On the other hand, for a meter stick moving with a velocity v relative to your frame of reference, let's say, you will observe the meter stick to have a smaller length than 1 meter. Now, there will be some Lorentz problems where you have to calculate time dilation and Lorentz contraction. And now the second part of the screencast has to do with energy and momentum. Just as space and time are different for different observers, energy and momentum are different for different observers. And there'll also be questions on the long kappa assignment involving energy and momentum.